We're good. Hi, and welcome to our 1 o'clock p.m. and final press conference, Ontario Water Contamination. Our participants are Claire Oswald, Assistant Professor in the Department of Geography at Ryerson University in Toronto, Kristen Leal, Master's Candidate at the Department of Earth and Environmental Science at the University of Waterloo, and Catherine Eimers, Assistant Professor in the Department of Geography at Trent University. Thank you.
Great. Thanks, Nancy, so much for inviting me to come and speak about our research. I have a very short presentation that will put our research project into a bit of a nutshell, so I'm happy to take questions afterwards. So the title of the talk I'm presenting tomorrow is Estimates of Chloride Storage Across a Gradient of Urbanization in Watersheds in Southern Ontario, Canada. And I do have several colleagues on this project, Stephen Oni from the Swedish University of Agricultural Sciences, and Chris Wellen from the School of Geography and Earth Sciences, McMaster University, and a student of mine, Greg Giberson. And what this title really means is that we are interested in knowing if chloride from road salt applications is being stored in watersheds. This is the main research question we're trying to address. So we want to know if the road salt that is put down in watersheds is flushed directly into streams, or if there's some lag because the salt is running into the environment and getting stored in the watershed. And there is research to suggest that this is happening. Previous research has found that chloride concentrations in streams are increasing. And from the data that we have been looking at, some historical data, we found similar trends. You don't need to worry about the details of these two figures. Basically what they're showing is that chloride concentrations are increasing over time in both urban and non-urban watersheds. And one of the really important things is that these the chloride concentrations are not only increasing in the wintertime, but they're also increasing during the summertime. And so this suggests that chloride is being stored somewhere in the watershed. And so we took a mass balance approach where we look at inputs and outputs of chloride from watersheds to figure out how much is being stored. And what this figure is just showing is that on the y-axis here, this is all storage numbers, so percent of the amount of salt that was put down in a watershed that is being stored. And all of the numbers, these points are all different watersheds, and they're all positive. So this is showing that chloride is being stored. Up to around 50% of the chloride inputs are being stored in the watersheds on an annual basis. And we do see a little bit of a positive trend as urbanization increases. So when you have a watershed that has more urban areas in it, okay, but there is a little bit of variability in the data, and that's some of the future research that we're exploring. So those are the two main results, that there are increasing chloride concentrations, and there is, in fact, chloride being stored in watersheds. This here is a map of the different watersheds that we are currently looking at. There are 12 different watersheds across southern Ontario. We've sort of focused on 3 areas, some watersheds that drain into Lake Simcoe, and a few in the GTA, the Greater Toronto Area, and a couple of watersheds in that drain into Hamilton Harbor. Our watersheds cover a gradient of urbanization. And this is a really important region to look at because the projected population growth is 14 million by 2041. So the Greater Golden Horseshoe is only going to become more urbanized, and these issues with road salt storage in the watersheds are only going to get worse. And just lastly, for a little bit more information about the methods that we took, I mentioned we used a mass balance approach, and really all that is that we calculated the inputs of road salt to a watershed, and we calculated the outputs of, we're specifically interested in chloride, so chloride coming out of the streams that drain those watersheds. And the difference between those inputs and outputs is what's being stored in the watershed. And we've done this using, basically doing a bunch of data mining. So we've created partnerships with the Ministry of Transportation Ontario, MTO, to get information about their salt usage and application on 400 series highways and other roadways in their jurisdiction. And we've also have access to an Environment Canada database of salt usage across the province. And to calculate chloride outputs from these watersheds, we've gotten data from conservation authorities, some municipalities, and we also use stream flow data from a variety of sources. So that's all I have to say now about our major results and methods, and if you have any questions, I'd be happy to answer them. Thanks. Okay.
No, okay. Great, so my name is Kristen Lee. I'm a master's candidate at the University of Waterloo, and I'm going to be showing just a very brief glimpse of a little bit of my master's research. And this is the title of the talk that I'm giving on Thursday, which is the ubiquity of artificial sweeteners in the aquatic environment. And I'm hoping to convey two main messages during the talk. First, that we're able to find artificial sweeteners in measurable concentrations in every surface water body that we look at. And that two, the detection and analysis of artificial sweeteners is becoming a really powerful tool for environmental scientists and watershed managers and environmental modelers alike to trace and track the influence of human wastewater in the environment. So I should give a little bit of background before I get any further. When I refer to artificial sweeteners, I'm exclusively referring to the 4 compounds that we analyze for, which are sucralose, cyclamate, acesulfame, potassium, and saccharin. So I'm only talking about those 4. I'm not talking about aspartame, which is what a lot of people think of when you hear sweeteners. I'm just talking about the 4 that we analyze for. And these 4 compounds are man-made. They're made in a lab, and so they don't occur in nature on their own. So when we do find them in nature, we know they must have come from a human source. And they're mostly used, artificial sweeteners, are mostly used in food products and personal care products. And they're used quite ubiquitously in consumer products, from diet soda to chewing gum to even things like children's medicine and mouthwash. So the average person, whether you're cognizant of it or not, you're likely consuming sweeteners on a daily basis, and that contributes a load. And the use of sweeteners so commonly and so popularly in the consumer environment, it's a really good way to kind of see the impact humans are having on the environment. And nowhere is this impact more, I guess, easily identified than in human wastewater. Because the unique thing about artificial sweeteners is that the body doesn't break them down. Acesulfame in specific is very useful because we can track it all the way from that can of diet pop that you drink to a river that receives wastewater treatment plant effluent. It doesn't break down when you drink it, when you flush the toilet. It doesn't break down when it goes through a wastewater treatment plant. So we find it in high concentrations downstream of wastewater treatment plants. But we didn't look at wastewater treatment plants. Research has already identified that as a potential pathway. We looked at small rivers and catchments across southwestern Ontario that didn't have wastewater treatment plants, that relied mostly on septic systems to treat their wastewater. The pink catchments are agricultural. The blue are the control catchments that we use that actually did have wastewater treatment plants, so we could show the difference in concentration when you have a municipal impact versus when you don't. The orange is a catchment that's rural, so it all depends on septic tanks, and the green are forested catchments. I'm going to just show you the agricultural data because it definitely kind of gives the biggest picture. These are a variety of agricultural catchments that have been identified as agricultural and predominant land use by the Ministry of Environment and Climate Change. And they picked these catchments as agricultural specifically because they didn't have anthropologic or human influence. And we showed by the presence of sweeteners up to a concentration of 86 nanograms per liter that all of these catchments have a human influence of wastewater. And so when you're finding sweeteners, yes, we're finding sweeteners, but you can also assume that you're finding other nutrients and contaminants that are associated with human wastewater, but we found them everywhere. And these are small catchments. They're very, very small. No towns or huge cities that live in these or are in these catchments, so it really is representative of those really small rivers and streams. And just to, I guess, show a little bit of a contrast, this is a catchment that we sampled that had 2 wastewater treatment plants. So the yellow dots show where the concentrations were elevated. So the highest concentration we found in this catchment was over 1,500 nanograms per liter. So you can see that difference, that even though we're not finding as much in small catchments, we can still pick up that source of sweeteners. So just, I guess, in some conclusions, like I said at the beginning, we're able to find sweeteners in almost every surface water body that we look at. And because we're finding sweeteners, we know that human wastewater is influencing every surface water body around us, from large rivers and streams down to small tributaries that run through agricultural areas. And that allows us, to ask more questions about what else is influencing these rivers and streams. It's not just sweeteners, it's, nutrients and other emerging contaminants that I guess we can be concerned about. And hopefully, I've converted you all to believing that artificial sweetener analysis and this detection method is a really powerful tool for us to trace human wastewater in the environment. The detection limit, so the minimum concentration we need to detect sweeteners, is 2 nanograms per liter, which is next to nothing. I guess to give a little bit of context, if you took a can of diet soda and dumped it in an Olympic-sized swimming pool, you'd still have 5 times their minimum. So we don't need a lot, which makes it really, really useful to use. Thank you for your time.
All right, thanks. So my name's Catherine Eimers, and I'm at the Department of Geography at Trent. And I am also very interested in how urban development is influencing not just water quality, but also water quantity, so how stream flow is manifested within southern Ontario. So some of our key findings, we found that urban influenced catchments in southern Ontario have very different hydrology. Precipitation that falls on urban catchments is delivered very quickly to streams. The streams respond very quickly. They have more frequent high flow or quick flow events, storm flow events. The height of those peak flows is greater, and they have less groundwater recharge. Urban environments are characterized by impervious surfaces, so lots of roads and buildings, and that, of course, is going to influence the potential for precipitation to percolate into the soil and recharge groundwater. In addition, urban streams are very flashy. So they respond very rapidly to precipitation events, and so they're a little bit more variable than their rural counterparts. So by virtue of that change in pathway of water or precipitation, the pathways have been altered in those urban streams. They're following more of a surface pathway as opposed to a subsurface pathway. That influences the quality of the water in urban areas as well. Most of our contaminants are deposited at the surface, and so that surface runoff is going to pick up more of those surface deposited contaminants like road salt. So similar to Claire's finding, we found that road salt concentrations are increasing in pretty much every stream in southern Ontario. And it's not just urban streams, it's also in rural streams, because of course roadways traverse pretty much every watershed in the populated part of southern Ontario. We've also found that chloride levels are increasing in every season, so it's not just when you're applying road salt to the roads in the winter and when they're melting off in the snow melt. Chloride levels are also increasing in the summer and the fall, the growing season, which is when you could project more biological effects because that's the growing season. And in addition, in the most heavily urbanized systems, chloride levels are already at or approaching, or have exceeded or approaching critical biological thresholds. So as background, vast majority of Canadians live in urban areas, and in Ontario this is particularly true. About 86% of us live, I shouldn't say us, Ontarians live in urban areas. And interestingly, the footprint of urban areas has increased quite dramatically. This is due to urban sprawl. So this is from Statistics Canada, and showing in Ontario and in Quebec, the footprint, the area of urban land has increased by about 80% between 1971 and 2001. That's because we're such a car-centered culture. We don't live near where we work anymore. We drive everywhere, and so that's expanding the boundaries of urban areas. So again, this is a great place to work, the Greater Golden Horseshoe. About a quarter of the Canadian population lives in this area. In fact, just 3 urban areas account for a third of the Canadian population. So Montreal, where we are now, Toronto, and Vancouver account for a third of the Canadian population, which is pretty staggering. So this is where we have a lot of population growth, a lot of urban cover, and we have this fantastic gradient of urban cover as well. So the red on this figure is showing areas with urban impervious surface, so roads and buildings, whereas the white is agriculture and the green is natural cover like forest. So we, again, mined existing data, used Water Survey of Canada data to look at stream flow across all these watersheds and found that those urbanized catchments like Highland and Mimico, Etobicoke Creek, Harmony Creek have very different stream flow patterns, far more frequent storm events, much more flashy, and much less base flow. We also looked at chloride using a different data set using the Provincial Water Quality Monitoring Network. So this is Ministry of Environment and Climate Change data. So they monitored a much larger number of stations compared with the Water Survey of Canada. And you can see that this is the greater Golden Horseshoe and the broader sort of outer ring, and not just urban catchments, but rural agricultural catchments as well. And chloride's increasing everywhere, 106 out of 116 streams that we looked at. Only 10 streams showed no change in chloride over time, but they happen to be some of the most urbanized streams already. So places like the Don River didn't show an increase over time, but you could argue that there's really very little space to expand urban cover within the Don River watershed. It's heavily urbanized, but it's been heavily urbanized for quite a while. So the significance, we're not expecting urban trends to change, to go downwards. If anything, it's expanding. So many of these urban areas are expanding at their periphery and sort of consuming actually agricultural land. So we can expect to see increases in storm flow in those watersheds and more flashiness. Chloride is also not projected to decrease at any time soon, but importantly, it's not just an urban phenomena. We are also seeing high chloride levels in road-influenced rural streams. And this may be an indicator, as Kristen mentioned, when we can measure something, we see it going up, we wonder about what are all the other things that we're not measuring. So it can be a good indicator of urban influence. That's it. Should I sit? Yes. Okay.
Thank you. Great, thanks. Now we'll move to questions. Are there any questions from any reporters in the room?
So my name is Kate Sheridan, and I'm a freelancer working with High Magazine in Vancouver. I was just wondering what other possible sources of chloride might be contributing to this phenomenon other than road salt. Are there any that you guys have noticed, or?
Okay, I was going to say wastewater treatment plant effluent is another important source of chloride. We also have point sources from like snow storage facilities, the road salt domes that you see around are the other important sources. I don't think it's been as quantified as carefully as, say, with road salt. Road salt's probably number one, but those are some other significant sources on the landscape.
Do you have any other questions?
Yeah. Are there any alternatives then? I mean, this is kind of an obvious question, but are there ways that people could be, obviously this is bad, right? Biological contaminants very bad. Are there ways that we can be reducing this other than reducing the use of road salt by finding alternatives or something?
Yeah, I'll jump in again. I know.
Question.
Yeah, I mean, the Ministry of Transportation is aware of the problem. Like, they have to obviously weigh public safety with the issue of road salt contamination. They have installed some like meteorological weather stations along the 400 series highway, so they're able to more get real-time data on weather conditions on the roads, so that they can send out the fleet when the road conditions need it, as opposed to sort of what's commonly done, which is just, okay, there's a forecast for snow, off you go with those big trucks. So they're doing a little bit of that. There are alternatives to road salt, like, so we're talking mainly about sodium chloride. There's calcium chloride, there's a beet juice derivative. There's a variety of different alternatives, but they're more expensive generally than sodium chloride. So again, it's a cost issue.
Are they using beet juice anywhere?
I've heard that it's being used in certain, I think maybe in Adirondack National Park, they've experimented with it. Yeah, okay. So certain small areas they've tried it, but I think it's, I think there's going to be a bit of a delay in that sort of being taken up.
And we have a question from the chat.
Sure, we have a question for Kristen. This is a question from Zapier Alip, who is a reporter from the McGill Daily.
Cool.
And the question is, why test for the 4 artificial sweeteners and not for aspartame?
So we test for the 4 that we test for because that's, I guess, the method that we've developed. It's a lab at Environment Canada that's developed it, and we've only really been testing for these since I think 2008 is when the first analytical method was developed. But we look at acesulfame over any of the other ones because acesulfame in specific is exceptionally resistant to degradation in the environment. So it persists for a very long time, and aspartame doesn't. It breaks down quite quickly. So in that case, we have, from environmental science point of view, we have a very small window that we can actually pick up that source, whereas with something like acesulfame, where we can find it, kilometers downstream from a wastewater treatment plant, it's much more useful to kind of look at that versus something that maybe doesn't persist for as long as something else.
And do we have any other questions?
So you guys, I have 2 more questions at least. You mentioned that you guys are using this as tracking other things that we find in wastewater. Can you expand on what other things you would expect to find in wastewater contaminated with fluoride or artificial sweeteners? Are they similar contaminants? Are they different contaminants? Theoretically?
If you want to go it. Well, there are like loads of different contaminants in urban areas, and they don't necessarily all behave the same, but I think there are things like if road salt is washing off roads, there are other things on roadways like hydrocarbons that can get washed off into our water systems. Like I guess road salt would be specific. Yeah, for roadways. I don't know if there's other major things on roadways that people are concerned about.
With the artificial sweeteners part, that's wastewater, and then there's a whole other host of contaminants that would be there, like hormones and medications.
A lot of other emerging contaminants that people look at, especially pharmaceuticals, are all things that we've been able to find downstream of wastewater treatment plants. I guess plugging my own research again, we like acesulfame over other emerging contaminants because it's so resistant to degradation. We just find it everywhere. And other emerging contaminants maybe necessarily don't have that same resistance. So we can use acesulfame almost as like a proxy to say like, okay, if we know we're finding this, you can pretty much count that you're finding other things.
Were there any more questions from the chat?
One last silly question. Are there any direct effects of these artificial sweeteners on the environment other than just serving as proxies? Presumably something. But
We don't know, which I know is a silly thing to say, but we really don't because these compounds they're all regulated and approved for use for humans by Health Canada. They're all regulated by Health Canada. But because we've really only been detecting for these compounds since 2008, 2009, it's still such a new field that we're really still in that stages of figuring out where it is and why it's there. And then we can kind of start figuring out, what the impact is on an aquatic organism. For acesulfame and for actually all the sweeteners, Health Canada has something called an ADI, or an acceptable daily intake, and it's a milligram per kilogram, so it's a mass by mass of how much you can consume. So for someone who weighs 140 pounds, they can consume about 900 milligrams of this stuff per day and be okay. But when you're dealing with smaller organisms that don't weigh 140 pounds, you need far less of that to have an effect. So we're still kind of in that stage now of figuring out what that impact is on aquatic organisms, which I think is going to be an interesting story.
Are there any other questions? Okay. There's a little delay on the list.
Okay. Yeah.
So.
I think it's neat to think about too that these sweeteners have been around for a long time, and we just are only now measuring them.
Yeah.
But, aspartame I think was invented in the 1950s.
Yeah.
So these compounds have been in our waterways. We've been drinking them without knowing it for a long time. It's just now we have the technology to detect them.
And we have the method too. Like that was, I think, the thing I was most surprised about was just how refined the techniques become. Like 2 nanograms per liter is practically nothing. And that's a testament to the hard work at the people in Environment Canada for developing this method. So
I think that's about it if we have no further questions. Okay, great. Well, thank you so much.
Thank you.
That concludes our press conferences for the 2015 Joint Assembly. Thanks for joining us. See you.
People must be sampling in the Great Lakes and in the oceans then.
Yeah,
It's been
they're,
around that long, right? You must.
yeah, so